Welcome to this explainer. Okay, today we're unpacking a really fascinating technical field test that gets right to the heart of a massive challenge in modern hardware design. We're looking at the Arad Connectivity MN54LM-20A Bluetooth Low Energy Module Test Report. If you've ever spent weeks pulling your hair out trying to figure out why your sleek new smart gadget just drops its connection out in the real world, well, you're going to love this. We are exploring the physical limits of Bluetooth Low Energy Module design and, more importantly, the ultimate engineering hacks to actually bypass them.
Here's our roadmap for today. We'll look at the size versus distance dilemma, the test field parameter settings, and module distance attenuation. Then, we'll dive into the power of rotation, external antenna advantages, and wrap it all up with key engineering points.
All right, part 1, the size versus distance dilemma. Shrinking IoT modules.
So look at the physical dimensions we're dealing with here. A standard MN54L15 series module sits at about 9.3 by 14.5 millimeters. But then you have Arad Connectivity's ultra-compact MN54LM-20A. That one shrinks things all the way down to just 7.5 by 10.2 millimeters. Now, in the world of hardware design, saving a couple of millimeters on a PCB, that is absolutely massive. It's what gives us sleeker wearables, tiny medical implants, and discrete sensors that blend into literally any environment. But as we all know in engineering, nothing comes for free, right? Every time we demand a smaller device, we're introducing a central conflict.
Which brings us to the million-dollar question. What is the exact impact of that size reduction on the effective connection range? That's exactly what this entire Arad Connectivity field test was built to figure out. We all kind of intuitively know that smaller antennas mean less reach, but exactly how much range do we lose when we start shaving away that precious real estate?
Let's find out in Section 2, Test Field Parameter Settings, setting up the real-world proving ground.
Okay, we need to break down the methodology here because the setup is really what makes this data so valuable. They didn't just model this in some sterile lab simulator. This was a rigorous outdoor test at Mazutian Riverside Park in New Taipei City, a totally open field environment. For the master device, they used an iPhone 7 transmitting at 0 dBm. That's a perfect representation of a standard everyday user scenario. The slave devices were the MN54LM-20A series modules, and they cranked those up to plus 8 dBm using standard 1M PHY mode, transmitting 4 packets per second at 20 bytes each. Now, to make sure the data wasn't completely messed up by ground interference or signal bounce, they mounted the antennas a full 3 meters high to get a crystal clear line of sight. Oh, and nature definitely didn't make it easy for them. It was a sweltering 33 degrees Celsius out there with 71% humidity. Literally the harsh reality where your products actually have to live and operate.
Moving on to Section 3, Module Distance Attenuation, the physics of miniaturization.
Now, what's really interesting about the hard data here is just how eye-opening the contrast is. The test engineers measured the maximum effective distance where a stable, bidirectional connection held up and at least one packet got through. With the standard-sized chip and PCB variants, they maintained some seriously impressive ranges. We're talking anywhere from 400 all the way up to 660 meters. But when you look at the ultra-miniaturized S-chip, the MN54LM-S20A, that communication range takes a noticeable hit. It drops to a maximum window of roughly 370 to 541 meters, depending on which axis you're measuring. I mean, that is a drastic drop. You're basically sacrificing a huge chunk of your reliable connection range just by shaving off a few millimeters of module size.
The engineers actually hit the nail on the head in the report, noting the reduction in physical volume directly impacts the radiation efficiency of the built-in antennas. It's literally a fundamental law of physics, and unfortunately, you just can't cheat physics. When an antenna's physical volume shrinks, its ability to radiate energy out into the world just diminishes. And that right there establishes a totally unavoidable baseline that every IoT hardware developer has to work with.
But hey, engineers don't just accept limits, right? We build around them. So let's get into Section 4, the power of rotation, engineering around the limits.
Okay, wait a second. Didn't we literally just say that shrinking the module inherently reduces the range? Well, yes, but get this. An absolutely wild 667-meter maximum distance was actually achieved with a chip antenna during these very same tests. How on earth did they do that? Not by changing the module itself, but simply by optimizing the module's rotational alignment. This is essentially the first major engineering hack they discovered out in the field.
So here's how you can actually use this actionable strategy in your next build. Step 1. Identify the directional constraints of your built-in antenna. You see, these built-in antennas don't radiate energy in a perfect uniform sphere. They have directional dead zones. Think of it less like a glowing sun radiating evenly, and honestly more like a flashlight beam with very specific blind spots, depending on exactly where it sits on the circuit board. Step 2. Apply physical rotation. The Arad Connectivity team realized that by just giving the module a specific physical rotation, specifically a 90-degree turn on the y-axis, they could effectively bypass those blind spots entirely. By pointing the strongest part of the antenna's radiation pattern directly at the receiver, they forced that tiny chip antenna to reach between 631 and 667 meters. It's a simple, completely cost-free, and incredibly effective way to maximize your range, just by thinking carefully about how your module physically sits inside your product's casing.
But what if you absolutely cannot optimize that rotation? Let's transition to Section 5, External Antenna Advantages, Maximizing Range in Tight Spaces. Because let's be real, for some applications, a built-in antenna just isn't going to cut it. Maybe your product has a dense metal casing that just kills the signal outright, or maybe the overall form factor forces the module into a rigid position with terrible directivity. In these cases, we have to weigh the awesome space-saving benefits of a built-in chip or PCB antenna against the raw, unadulterated power of attaching an external u.FL antenna like the P111B24003 model they used in this test.
The test proved definitively that if your IoT product is severely space-constrained, but you absolutely have to have maximum transmission range, this external u.FL antenna is your ultimate fail-safe. By routing the signal out to that external antenna, the MN54LM-20A module provided incredibly stable connections up to 661 meters along specific axes. It completely offsets the range degradation caused by shrinking the main module. You get to keep your tiny PCB footprint on the main board, but you outsource all the heavy lifting of the signal radiation to an external component that can actually breathe properly.
Okay, we have covered a lot of ground today. Let's wrap it all up and distill this entire test report down in Section 6, Key Engineering Points, wrapping up the data.
If you are designing the next generation of IoT hardware, these 3 actionable pro tips absolutely need to be on your drawing board. First, shrinking your module volume reduces built-in antenna radiation efficiency. Always account for that trade-off and plan your link budget accordingly, because again, you can't cheat physics. Second, never ignore physical placement. A simple 90-degree y-axis rotation can instantly fix a dead zone and restore immense range without adding a single cent to your manufacturing costs. And finally, third, when internal space constraints inside your device are just too strict, routing your signal to an external u.FL antenna remains the absolute best alternative to guarantee maximum range in remarkably small spaces.
Which leaves us with one final thought for you to ponder. In this relentless race to make devices smaller and smaller, how will you balance physical size and connection range in your next IoT hardware build? Are you going to rely on the clever geometry of physical rotation, or will you offload the hard work to an external antenna? Engineering is really the art of the perfect trade-off, and this data from Arad Connectivity gives you the exact blueprint to make the right call. Thank you so much for joining me for this explainer. Keep innovating out there, and we'll see you next time.